Hi, everyone. My name's Shellen McCoy, and on behalf of the Atlantic Salmon Conservation Foundation, I'd like to say welcome to today's webinar. Of course, the series is possible because of the help of the Government of Canada. So for today's webinar, we're really pleased to be hosting today Michael Arsenault. Michael is a fisheries analyst with the Wolastoq Nation in New Brunswick, where his main responsibility is researching various fisheries related issues and informing the 6 communities of the Wolastoq Nation. He received his Bachelor's of Science in Wildlife Ecology from the University of Maine and his Master's of Science in Biology from the University of New Brunswick. He'll be speaking on remote analysis of stream road crossing in the Wolastoq Watershed. So for this afternoon, Michael's going to do his presentation. At the end of the presentation, we'll allow about 15 to 20 minutes for questions and answers, and I'll moderate that part of the session today. So for right now, I'd like to turn it over to Michael so he can start his presentation. So Michael, welcome.
Thank you, Charlene. I appreciate it. So as she said, I am Michael Arsenault. I work for the Wolastoq Nation in New Brunswick. About 2 years ago, I decided to apply for some research funding through ASCF, and thankfully I was accepted. And we decided to extend my master's research into the Wolastoq Watershed, otherwise known as the St. John Watershed, and to look at remote analysis data using LiDAR and DEM. So I'll be talking to you about that today. So to start off, the broader scope of this project is looking at the impacts of barriers. We know that fragmentation of aquatic ecosystems are a major cause in the decline of populations of fish. This can be due to culverts that are failed, or crossings that aren't up to code or have just higher slope, and this will result in essentially lower biodiversity, lower habitat usage due to access issues, and lower nutrient exchange between the upstream and downstream ends of the barrier. Most commonly, these barriers are anthropogenic in-stream structures like culverts, but they can also extend to non-anthropogenic stuff like natural structures like beaver dams, and stuff that actually doesn't cross roads like weirs. In the past couple of decades, a significant increase of road networks has been shown, and it's shown to be forestry activity to be increasing even further, increasing those road networks even more. So we know that more road networks most likely means more stream crossings, which is going to result in possibly more barriers. So to give you an idea of how a culvert, like a high slope culvert, would impact stream crossings and the downstream side and upstream side. So if you have a culvert that has a high slope, let's say 5–6%, it's going to be increasing the velocity. It's going to be increasing, it could be restricting the channel flow, which would also increase the velocity, making it almost impossible for fish to pass up due to that velocity or due to water level within the culvert. This would result in the material and nutrient flows, where you're not getting any sediment transportation downstream. You're not getting macroinvertebrate transports, like you'll have macroinvertebrates try to go upstream and drift down, and they can't do that now because of the inclined culvert, and because of the passage of these culverts, fish can't spread to their full extent of their habitat, which reduces biodiversity, survival, and feeding options. So these are just essentially the background of what culverts can do physically to the surrounding environment. As you can see here, this is a pretty tame example, but the culvert was obviously put in with no consideration to stream width. So you can see it's probably about 20–25% reduction in stream width, which would increase velocity. They would probably do this because it would raise water levels, but in more extreme examples with higher slopes, it may raise the water level to such a high limit where the velocity would overcome a lot of swimming speeds from fish. And that would cause is a lot of downstream erosion from that velocity, which would also just impact it or result in a hanging culvert. So why do these barriers matter to First Nations? When I work for the Wolastoq Nation in New Brunswick, we have to tie this back to how barriers impact that. And one of the big things is within the Wolastoq Nation territory, Atlantic salmon and brook trout are vital to their culture, their sustenance, and well-being. And a lot of these barriers directly impact those rights because of what we talked about in the previous slides was the lack of biodiversity, lack of habitat, variability, and inter and intrapersonal competition. So that all results in that would have a population decline and cause these populations to probably go extinct or extant, like to local regions. Barriers to fish passage will cause irreparable harm to First Nations through ecosystem health degrading, lack of fish and sustainability to practice their food, social, and ceremonial rights. We are seeing that to this day, where Atlantic salmon we are not able to collect Atlantic salmon for cultural reasons. And a lot of the communities I represent have voiced this concern with multiple species, Atlantic salmon, brook trout, and other diaphragm species. Another one is dietary deficit. There are a lot of studies out there that show that people who in the First Nations who fish for sustenance for fish aren't able to do that anymore just because of the population decline, loss of economic opportunities. Even when it comes to non-endangered fish or non-threatened species, a lot of this could be looked at like glass eel economic opportunities. These barriers do affect those kinds of populations besides, the most popular ones like salmon and brook trout. And this all results in degradation and loss of connections with their culture due to that. Because if they can't practice their rights, then it eventually just fades away. And we need to preserve that. So our first step in this process of trying to maintain and improve the habitat variability, the biodiversity, is to look at how or where these barriers are. So within the Wolastoq Watershed, there's no barrier analysis. We have private forestry companies, they'll have their own data sets that are often not shown or not publicized. The DTI would have small crossings of when they were installed, but otherwise any current evaluation of stream crossings is moot. And the Wolastoq Watershed is approximately 55,000 square kilometers. Getting field crews out there to do these evaluations in person is just not viable, especially when you're looking at over 8,000 crossings. And that's just the tip of the iceberg with publicly available data. But as my master's research has shown, that we can use new techniques in GIS and LiDAR to evaluate these crossings remotely and find the best bang for your buck, essentially, of what culverts we can target to remediate and restore the most amount of habitat, or what is most important culturally or economically to the First Nations. So to break it down to objectives, we need to identify and classify high stream order crossings that are potential barriers. And this is done by essentially finding the intersection between the streams and road networks. And the reason for the high order classification is because when you're looking at remediation targets, you don't want to go spend a lot of time looking at first order culverts that are on really small stream systems that only block 1 kilometer of headwater habitat. you'll want to be looking at the larger culverts or larger crossings that are blocking off 30, 40, 50 kilometers worth of habitat. Because if you're going to do these offset projects, if you're going to be doing these remediation projects, you're going to want to get the bang for your buck. It's the most practical. And then determine the number of linear kilometers upstream of that barrier, and then create brief reports of each of those. And we decided to go with between 100 and 150 of these reports that will outline the location, the nearest access point by road, what type of barrier it is, the slope, elevation difference, and possible solution. Possible solution would just be 1 or 2 sentences being like recommended, like full replacement. It would be more up to engineers to go beyond that. So what we found was using the GeoNB data, it came out between 8,340 crossings when you're crossing the stream and road networks. We expect this number to be probably very conservative, just due to the quality of data. A lot of the time, road networks are probably about 50% of road networks aren't mapped. A lot of public or a lot of private industry will have those maps, are usually unwilling to share it. So we decided to use the GeoNB data since it's the most publicly available one and people can access it. And we broke this down by stream order. And what you can see here is most of the crossings are stream order 1 and 2. And that's just because you'll have a lot more channelization towards the higher order streams. So we're going to be focusing on stream order 8, 7, 6, and 5. So once we have all these crossings, how can we classify them remotely? And this is just an example of what a bridge would look like. Off to the left, you'll have the LiDAR DEM overlaid with a hillshade. And as you can see, the way we have an automatic classification process that is yet to be published, but I'll give a quick explanation. Essentially, is that it finds a crossing and makes a little buffer, and it uses certain characteristics of that crossing to determine whether it's a bridge or not. Of course, we can do this manually where we see the road has steep drop-offs in elevation on both upstream and downstream side. And if you're using the DEM provided by GeoNB, it's already essentially carved. It's burned where they'll split the bridge to allow the water to virtually pass through. But we have algorithms now that does a lot of pattern recognition and rasterization algorithms to determine what crossing this is automatically. This is a good example of a false detection where either the stream network was derived where we call too sensitive, where it thinks there's a stream there, but it isn't. And that's usually a representation of like ephemeral streams. We want to avoid these. Ephemeral streams are usually not used for fish passage that often, or wouldn't be a high priority. A ford looks pretty similar to a bridge, but you can tell by the road embankment, it slowly tapers off on the upstream and downstream side instead of having a steep drop off. So when you're looking at the crossing, you're always looking at in the algorithm, it's essentially percent base changed over a seeding process, which takes each one of those little pixels and measures the 16 pixels around it and does that over and over and over again to determine percent change of elevation to determine whether or not it is a ford or a bridge. So once we have all this classification done, we can finally order by stream and what types of crossings. And it's a lot of numbers, but essentially a lot of the culverts, a majority, I would say almost half of all culverts are first order streams. And that's mostly made up of first and second order. But then as we look at the larger ones, we're going to want to target the anything above the 5th order for culverts, fords, and impoundments. And impoundments would be just considered something that doesn't have a culvert, but is still a crossing. This could be a weir, this could be a beaver dam, this could be an actual dam. And it's just another representation for it. As you see, it's heavily weighted to the lower order streams in terms of crossing number and culverts. So once we have all these culverts once we have all these crossings classified, we can finally look at how do we evaluate them? What determines a barrier and what determines a passable crossing? So we can start with the culverts since they're most abundant. I use a method that from Dable 2014. He worked for Wisconsin DNR, and this method shows that you take the upstream and downstream elevation, and you can get the length of the culvert from each side of the road embankment to get the length of the culvert. Therefore, you can get the slope, and that's probably the most important part because slope determines passability, or will heavily influence variables that will be highly correlated to passability, like water velocity and water depth. So looking at fords is a lot more difficult in terms of evaluating whether it's passable or not. And this one, I think, is the perfect example of like an edge case where we see that off to the left, you have your LiDAR DEM, and you can see that a lot of the landscape is petering off on the crossing. The upstream and downstream side looks passable, but you can see there's probably a heavy amount of erosion. Off to the right, you can see there's a clear cut. The roads probably aren't maintained, and this realistically could be impassable by now since this LiDAR was collected in 2016, I believe. But this is one of the difficulties in evaluating passability of fords. But in this case, I would flag this as needing remediation since there is no bank reinforcement, there is no structures in place, and obviously you can see by the elevation, the lower elevation flushing out beyond the stream, that's becoming more of a mud area and is probably experiencing high amounts of sedimentation or erosion. This is another edge case, and I like to provide these just because it gives something for people to think about. This is a properly done ford in the sense of they reinforce the embankment on both sides, as you can see up to the right, but even in the LiDAR, you can see, in the ortho, you can see the channel restriction. I wouldn't consider this adequate. This would be flagged and would need to be remediated. The bank reinforcement goes way too far in and restricts the channel by over 50%. That is not up to code for water course alteration guide, and usually that's our guiding principles for these kinds of evaluations. And one last one where I would accept this one as passable, where you can see reinforcement embankment on both sides. You can look at the LiDAR, and there's no petering off of elevation beyond the stream channel. So realistically, there's probably no heavy erosion happening, and they have the reinforced embankment. Water levels look low in that ortho, but we can't make assumptions for that kind of thing. So I would consider this one passable. And then lastly, evaluating impoundments. This is always a tricky one where we have to identify whether if a culvert's actually there. Our framework shows that there's a crossing, but sometimes the way stream networks are derived, if you have two large water bodies and a small strip of embankment, it'll still be able to track it through. So usually you'd have to go in for a manual inspection, or you'd have to increase your algorithm's range to figure out if there's an actual culvert there or not. But this would be considered an embankment where the upstream and downstream side have no visible crossing, and this would be flagged as a barrier. Oh, one more. This would be a weir. It looks like a weir. I've never been here, so looking at it just remotely, you have your bridge off downstream, and then upstream directly you'll see the concrete weir, and I would consider this a full barrier, full stop. If you take the elevation difference between the downstream and upstream side of that barrier, it is 16%. Obviously not passable to any fish. Most fish can't pass beyond 4%. And this would either have to be remediated, but a lot of the times with these impoundments, we don't know why they chose these designs. So it's more of reaching out to either municipalities or federal organizations like DTI or something to explain why this structure is in place so we can further the remediation. So something to give you a visualization of actually getting the upstream and downstream lengths of culverts. The way that you can manually do this process is you take your LiDAR DEM and you overlay it with the hillshade, and essentially you can take your upstream, you can just create a point file, and you find the lowest elevation on the upstream and downstream side, create points there. Usually the golden rule is if you're, I think it's 2 to 5 pixels away from the road embankment, you should be 2 to 5 pixels on the upstream and downstream side, and 1 pixel equals 1 meter. You place your points and have a line connecting them, and you therefore can calculate the elevation difference and have slope. So once we've determined all of our slopes, our locations of our impoundments, the classifications, now we have this giant list of barriers and slopes. So what do we do with them? I always look to the literature for this. Off to the right, you see 6 species that are either present in New Brunswick or one day will be, or just species of concern. So you have weak swimmers like burbot and lake chub, and also diagenous fish such as blueback herring and alewife fall into this category of weak, really weak swimmers. They pass at between 2% and 2.5%. And then on the more popular species, I would say just more significant species in this framework is Atlantic salmon and brook trout, where you have 4 to 4.5% as a threshold, and then brown trout not present in a lot of areas, but could be one day, and they would be considered one of the strongest swimmers at 5%. And so when we digitize those culverts or we look at impoundment or something, if there is a slope over 5%, you know it's a definite barrier. But it becomes more nuanced according to what the user or manager's goals are. If they want more bait fish, or they want more secondary species, or accommodate for the weakest swimmers like alewife, they would want something that's 2%, 2.5% or less. And so the number of barriers would directly differentiate between those. And then of course, we can't really measure the slope. We can't digitize stuff like the impoundment we saw between 2 big water bodies or a ford or even a dam. So we consider the ford being an evaluation based process where you look at LiDAR and the ortho and focus on the watercourse alteration guide to determine whether it's a barrier or not. An impoundment is always considered a barrier, and a dam is always considered a barrier, unless there is specific fish passage, like a fish ladder at bigger dams. So once we determine what is a barrier, what is not, based on the manager's criteria, we can now write a report. So the end goal of this is to have between 100 and 150 reports of, well, 100 to 150 crossings, and develop a report for each crossing. And each crossing will look, or each report will look very similar to this, right? You'll have your orthophotography that is publicly available on GeoNB that can be accessed by anyone. So if you want to like scope out the area even more, that's possible. Give you the coordinates for it, the crossing type, the length of the culvert, if it's a culvert, the slope, and the upstream kilometers it's blocked off. So this is one example that I thought was pretty apt, is that it's a 5.3% slope, and there is some vertical error in this DEM. I think it's 10 centimeters. But even making the assumption of that, we're still falling above the unpassable mark. And if you look at the orthophotography carefully, I should have blown it up. It's a hanging culvert. You can see the bottom lip. It's impassable to fish. So after this, we've determined that in the report, we can just measure the upstream kilometers. It's a basic function in ArcGIS. You can just do a trace analysis and find the total linear kilometers. And an important point, the thing to point out is linear stream kilometers and habitat are not mutually exclusive. You can have wetland areas, you can have bogs, you can have riparian zones that frequently flood. But for the example of this, to just give a standard metric without going beyond wetland classifications and stuff, we use linear stream kilometers to kind of prioritize. So, and then off to the right, you can see that we summarized culvert slope exceeds threshold for all fish species of concern. Orthophotography shows it as a hanging culvert. A full replacement is recommended. Again, we never go into details. That's up to the proponent to decide the engineering details. I'm not an engineer, I am a biologist. So some limitations to this project is that LiDAR DEM is a snapshot in time. That some data is 5 to 7 years old, and things have obviously changed. And we're working towards solutions for that, where we could say, well, this culvert is passable, but that was 7 years ago, and it could be blown out by one of many major storms or thaw or lack of maintenance. And this is probably one of the things that we're looking at next, is trying to predict what culverts will fail based on variables such as soil type, erosion risk, what we call a stream power index. And crossings can be missed based off the quality of data. So this framework shows you that the data quality you put into the program is what you get out. Having only half of the road networks presumably mapped, there is a need for an automatic or even manual process, which take a long time, of mapping these roads using DEM as your guide. As you saw in the DEM snapshots that I showed you, road embankments are really easy to identify, but finding some kind of automatic way to do it for such large areas like 55,000 square kilometers is still a work in progress, and there are some worthwhile researchers out there that are pursuing this. And lastly, stream road crossings are not the only barriers. So we have beaver dams, weirs, something where there is no road that crosses it, so we're missing it. And a solution that we're looking into for this would be more of a using the stream as a guide to determine passability, what we call a NIC zone analysis. And it measures elevation change over distance, and the user will specify certain thresholds, like 2-meter change over 2 meters or 2-meter change over 5 meters. And if it does, it will create a line, and that'll be what you call a nick zone. And that seems to be a good solution for determining this. But again, beaver dams are created every year, and if they're torn down, they can be rebuilt again. So having this be a snapshot in time is a big disadvantage. And we're trying to figure out how to predict these kinds of nick zones. In conclusion, the framework identifies anthropogenic barriers based on fish passability and managers' choices and metrics. So the number of barriers will greatly vary depending on what the manager's remediation goals are. Like if you want alewife to pass everything, you're gonna have a lot more barriers than you want for brown trout passing. And by having all of those reports of, like, let's say 100 to 150 crossing reports, is going to allow First Nations to locate areas of interest to remediate. So if they find particularly like important cultural site or an old harvest ground or something that they want to restore, this kind of analysis is perfect for that, where like, well, we're missing 75 kilometers of habitat, and that they know that their ancestors used to fish there, so they would like to remediate it. So we can focus on funding projects and other remediation efforts and partnering with other organizations to do this. And one of the more important uses of this is the offset. So Fisheries Act authorizations and projects require offsets, and often the proponent or regulator will propose the offset, which is just a remediation project. And oftentimes the First Nations will have to be consulted on this and review it, but we want to be more, I guess, we want to be the ones that are proposing these offsets for the benefit of the First Nations, to reinforce their culture and their sustenance feeding, their food, ceremonial, and social rights. And by having this list of offsets, they can propose as a First Nation for these offsets and make a larger impact to them comparatively to just some random culvert in the middle of nowhere. And that's it. Any questions?
Well, thanks, Michael, for that presentation. So yes, now we are opening the floor to questions. You can always type it in and I can read it out loud, or if you want, you can click on the little hand and I'll unmute you and you can ask your question. I see a hand already. So let's see here. I'm gonna unmute. I think you're good to go.
Okay, thanks. Can you hear me?
Yeah, I can hear you.
Oh, perfect. It's Pat Nussey from Nature Conservancy Canada. Thanks, Michael. That was a really great presentation, and you know, really nice to see that there is some possibility of assessing culverts remotely, because obviously it is a ton of work to do this in the field. But my question is, if you've had enough time or chance to compare the desktop results for passability to an actual culvert field assessment and determine, you know, how accurate it's been, particularly with the slope measurements, if you're getting a fairly accurate reading from the DEM versus what's calculated in the field?
Yeah, actually we have a publication that came out at the beginning of this year. I'm not sure if I can post it anywhere, but yeah, I published my master's work on that, where we looked at the Restigouche crossings, and it showed that there is no statistically significant difference between field values and remote values. But you're also looking at New Brunswick having really high quality LiDAR. I think it's like 3 to 5 points per square meter. It's 1 meter resolution. Recently, I've done stuff in Quebec where it's a little bit lower resolution, and we found some notable differences, but we're trying to work through that. It is possible for even lower resolutions.
And you're coming to the same passability score. The end result is basically the same: partial barrier, barrier, no barrier.
Yes, yeah. Once we account for, if we categorize it like that, absolutely. I think it's above 90% acceptance on if we classify barrier, no barrier. But if we do exact slope percentages for lower resolution, let's say 2 to 3 points per square meter at 1 meter resolution, you'll start to deviate away from that.
Great, thank you.
Okay, is there any more questions? I'm just looking for some hands or anybody to type something in. Okay, we got something typed, so I'm going to attempt to read it out loud, Michael. It says, my understanding was that LiDAR is still not able to go through water. If that is still the case, how do you tell whether the up and downstream elevation is being taken at water surface or culvert structure?
So there are two ways of looking at this. It's measuring stream bottom. It's a bare digital elevation model. It's a bare surface model. So in high resolution LiDAR, you can look at, sometimes if the culvert's big enough, large enough stream order, you can actually click the top of the culvert within the 1 meter pixel range. But often you just click once downstream and then once upstream, and you can assume that the immediate upstream and downstream area will be indicative of the slope, like culvert slope. But sometimes, yeah, it's for smaller stream orders, it's a lot harder to tell. But in terms of like water, we don't know the water depth. We don't know, we just know the stream bottom or the lip of the culvert if it's big enough.
Okay, thank you. A couple of hands. I'm going to give it to Thomas Sweeney. Here we go. Oh, go ahead.
Simple in something similar in Nova Scotia. We're just having trouble differentiating between open bottom culverts, kind of follow from last example, where you still have that slope in the bottom versus ones that have concrete as well as bridges. They seem to look very similar in most data sets. How are you able to differentiate between those?
Yeah,
that's okay. I wouldn't blame you.
Yeah, no, it's that is a really good question because I'm actually working on this right now. We are having issues with, I recently did some stuff in the Gaspésie like peninsula where they have some really good engineering there. I don't know why. It just happens to be that they'll have the open bottom culverts or a concrete slab bottom, and it'll be perfectly flush with the stream channel. But you can still tell that flow is being altered from one side of the embankment to the other. So if you have a post-process DEM, it'll be a lot harder to tell. But if you go from point cloud to DEM, if you're not getting immediate shifts in elevation, so I use a pattern recognition program that I created that shows the elevation difference between each pixel, depending on where I quote unquote like seed the program. And with bridges, you're gonna get like, I think it was like a 50 to 80% like increase in elevation change immediately over 1 meter. But for a open bottom culvert, you're actually gonna have, you'll see a lot of them have like a 45-degree slant towards the road embankment. You'll see some like distortion, or you'll see it change by 50% over 3 meters instead. And it's just kind of fine tuning the thresholds for what determines the edge of a road embankment is the way I approach it. But I'm still messing with it because right now it's a lot of the time it's unique to the crossing, and that's what my algorithm is struggling to figure out. But we're working on it.
No, that's super interesting. Thank you.
Okay, so next we have Natalie Becerra. You can unmute. You go right ahead.
Oh, okay, thank you. Great presentation, Michael. I was wondering what if there are next steps in terms of field truthing the data. I know from experience, having done culvert assessments in the Nashwauk, which is a sub-watershed of the Wolastoq, that a lot of the modeled data in New Brunswick for kind of, the big bang for your buck culverts often overlooks larger culverts or double culverts or even triple culverts in some cases. They're often misclassified as bridges. And I guess you may have addressed this in your previous point where you spoke about, looking at slope, which can help you differentiate between a culvert or a bridge. But I was wondering, in terms of next steps for field truthing, what plans there might be.
Right now, in the future, we're looking at flow patterns. Essentially, like the stream power index is probably the next big thing to field truth, and that would actually solve a lot of problems with distinguishing crossings. So a stream power index, looking at each individual 1 meter cell, it'll have a specific value, and being able to identify what kind of flow pattern is going into where, you can distinguish whether it's a single, double, or triple culvert or whatever, because the stream power will deviate between those three, because you'll essentially have three what you call like sinks in one side of the road embankment. But I'm still trying to figure that out of how to do it. I think machine learning is probably my only option right now, and we've had success with that so far. But that'll be the next thing to field verify.
Okay, awesome. Thank you.
Okay, we still got some time left for today's session. If there's any more questions, I'll give you guys a minute or less. Okay, so I think that's it for today's question, but there's always ideas. Oh, just a sec here. I have a text come in wondering if I could share your contact information, Michael. So for those that want further dialogue or have any questions after the session today, feel free to email me and I'll forward that to Michael, and you guys can connect if that works, and we'll be able to share that. And for anybody that missed today's session is recorded, and we will be posting it after in the next hour, and it'll be on our YouTube page, so you can always go back and view and listen, or share it with someone else to come in and to listen. So once again, Michael, we just thank you for today and taking the time for sharing all that information. And I also want to mention that we do have in the new year another series of webinars coming up. January 11th is the next one with Kurt Samways, and he'll be talking on Parks Canada Research Chair studying salmon along a natural gradient of recovery. So once again, thank you to Michael. Thanks for everybody else for joining us today and participating. And you all have a good day and also a Merry Christmas. So we'll talk to each other soon. Thanks.
Thanks, Charlene.